holes explained. Now before we start the video, let me give a quick recap of what we learned in the previous episode. First, we covered basic information about what is a black hole and other details. Then we covered the history of black holes, like who discovered black holes, when and how. Finally, we figured out the formation scenarios of a black hole, how it formed, the condition needed, etc. So now with that in our mind, let's start our video. Now, moving on to the types of black holes. Generally, black holes are categorized on the basis of their mass into 3 to 4 categories: stellar, intermediate and supermassive, and the less commonly known ultramassive black holes. Stellar black holes are black holes with masses ranging from 3 to several tens of solar masses, with most of them being between 5 to 20 solar masses. Intermediate black holes or intermediate mass black holes, also known as IMBH, are black holes having the mass of about 100 to 100,000 solar masses. Supermassive black holes or SMBX are black holes having the mass of from 100,000 solar masses to tens of billions of solar masses. I would like to give an example of a black hole named Ton 618, which has a whopping 66 billion solar masses, which makes it fall under the category of both supermassive black holes and ultramassive black hole. And finally, ultramassive black hole, which refers to black holes ranging from greater than 5 billion solar masses, with most of them ranging from 10 billion to 40 billion solar masses, with a few monsters lurking in the upper side of even that. Latest research suggests that black holes dubbed stupendously large black holes, also referred as slabs, with masses greater than 100 billion solar masses could possibly exist, such as Phoenix A, with a staggering mass of 100 billion solar masses, a total beast. Although sometimes it is also referred as an ultramassive black hole. Other than this, there are 4 types of black holes based on charge and angular momentum, that is spin: a Schwarzschild black hole, a Kerr black hole, a charged black hole, and a rotating black hole. The Schwarzschild black hole is a type of black hole having absolutely no angular momentum and charge. This is the simplest type of black hole. A Kerr black hole is a type of black hole having angular momentum and no charge. A charged black hole is a black hole having charge, and a rotating black hole, as the name suggests, is a black hole having spin, that is angular momentum. A Kerr black hole is a type of rotating black hole. Each of these black holes have a delineating equation. For example, a Kerr-Newman black hole accompanies the Kerr-Newman metric, where the black hole has charge and angular momentum. The Schwarzschild black hole has the Schwarzschild metric. A charged black hole has the Resnier-Nordstrom metric. And finally, a rotating black hole has the Kerr metric. Sometimes, few black holes can have 2 or multiple solutions also. Also, there is a categorization of black holes based on the compatibilities of the 3 inherent properties, that is mass, charge and angular momentum. This is called an external black hole, a black hole that has the minimum mass compatible to the charge and spin. Similarly, if a black hole has more charge and spin than a black hole of its mass should, then it is known as super extremal black hole. There is also a near extremal black hole, which is a black hole that is not far from the minimum possible mass compatible with its charge and angular momentum. Many super extreme black holes might not have an event horizon at all. therefore featuring its singularity. This is prohibited by the laws of nature. That's why it remains highly speculative that whether these objects exist or not. If, for example, a black hole has the same mass, charge and angular momentum, also known as spin, like an electron, then it will also behave like an electron, inheriting its properties like its magnetic moment or its magnetic strength. Though this hypothesis, known as black hole electron, is a hypothesis, and this would be classified as a super external black hole and might have a naked singularity, which is prohibited by the cosmological censorship principle, which we will cover later in this video. Recently, a theory has arisen to the public regarding cosmological coupling, which states that the mass growth of black holes is linked to the expansion of the universe itself. This states that dark energy comes from black holes. Dark energy is a type of cosmological constant which expands the universe. A cosmological constant is a coefficient which is responsible for the growth and expansion of the universe, first added to the field equations of general relativity by Sir Albert Einstein, which he later removed, calling it his greatest blunder of his life because he thought that the universe was a static, fine-tuned universe. But according to recent observations, the universe isn't static, nor is it. So, the universe is expanding, so actually it was correct. So, it is thought that the dark energy is vacuum energy, which are quantum fluctuations which arise around space because space cannot be a perfect vacuum and there are always 0-point fluctuations occurring now and then. And this arises due to Heisenberg's uncertainty principle. Also, vacuum energy is affected along black hole's mass. So, therefore, cosmological coupling is observed. Also, black hole may be a secret gateway to traveling all across the universe. Do you know how? These are known as wormholes. These are basically tunnels which allow you to travel across space in absolutely no time. But there are always different types of wormholes, which is a topic for another video. Black holes are pretty abundant too. According to recent calculations of the probability mass function, in every cubic megaparsec of space, there is 50 million solar masses worth of black hole, which basically means that black holes, especially stellar mass black holes, are pretty abundant. There is a maximum limit for angular momentum of black holes because as the black hole is spinning, the ergosphere flattens, and if the ergosphere, which we will explain later, flattens too much, then the singularity would seemingly be visible, which isn't allowed by the cosmic censorship hypothesis, which was formulated by Sir Roger Penrose. And a black hole named NGC 1365 is spinning at 84% the speed of light, which is the maximum limit for the spin of a black hole, as per the cosmic censorship hypothesis. Because if we go any faster, the singularity would be seemingly exposed, that is a naked singularity, which is prohibited by the laws of nature. Any curved black hole faster than that would be a fast curve. Now let us cover the different regions of a black hole. First comes the accretion disk. The accretion disk is a region where, as a result of the high speed of the objects coming in, are forced to circle around the black hole for a particular period of time. Thus, the objects are extremely hot so they emit black body radiation as a result of friction. Black body radiation is the radiation emitted by an object at a particular temperature. The accretion disk isn't necessary because in order for an accretion disk to be born, generally a huge TDE has to occur, that is a tidal disruption event. Also, in order for an object to enter the event horizon, the object has to go through generally an accretion disk in a tough path known as the 10x line. Second comes the event horizon, which we have already covered in our previous episode, so I won't talk about it much. The third is the innermost stable circular orbit, or RSCO, where objects in the accretion disk don't fall towards the point of no return. Instead, they orbit around the black hole. The object is still falling into the black hole, however, the acceleration is enough to contract the gravity. This principle applies to all objects, and it is generally 1.5 times the radius of the event horizon. We will dwell into the rest of the regions in another episode. Stay tuned for more. If you found the content of the video interesting and captivating, kindly show your support by liking, sharing and subscribing my channel. If the video is not to your liking, you may as well dislike. See you soon in my next video of the same series, The Mystery of Black Holes Explained. And as always, thank you for watching.